Welcome, Year 12s. As you know, I'm sure, I've been looking at second derivative this week, and I was looking through 3D part 1 where you practice finding second derivatives, and I stumbled across question 14, and it's quite an interesting function. It's a logistic function. I think it'll be worth looking at. Keep in mind, though, that your main focus is really trigonometry at the moment. However, I thought if you can find the second derivative of this and use it to find an inflection point, then you're in pretty good shape. And I wanted to go through this question. But before we get to the second derivative, the question asks, I've got my book here, find the y-intercept. Okay, y-intercepts. And that always happens when x equals 0. We've got a logistic function, so x isn't x, it's t for time. So we're looking for an f of t equals 0. All right. Now, if that t there in the function equals 0, then we will end up with e to the power of 0, because 0 times minus b is just 0, and anything to the power of 0 is 1. So we're going to be left with this. Right? So let's change colours. All of that there will equal 1. Right? And I'm going to try and just undo that drawing if I can. Oh, there we go. Because I want to keep that function as it is. Okay, these logistic functions, really interesting. Oh, we're in green, that's right. The y-intercept here, c on 1 plus a, they're used to model population growth in a more realistic way than just looking at an exponential. Because in real life, populations don't just grow forever. They will have something that limits their growth. Right, so maybe, I don't know, you've got mice and they're growing, but eventually they run out of food. Yeah? They will have this upper limit. There's a limit to resources or space or whatever, right? Or maybe there's a predator. And you can see you kind of get this S-shaped curve which taps out at some point. As time goes on, population will reach an upper limit, right? Can you see the concave up shape here and the concave down shape? And somewhere in here there is what? A point of, you guessed it, inflection, right? Where we change from this increasing gradient and then the gradient starts decreasing. We change from concave up to concave down. Okay? Erase. I need space for the next part. The next part says, show that y equals c is the horizontal asymptote. Okay. We're saying that f of t equals c, right, is horizontal asymptote. Why is that? Well, I think I'll just focus on the bottom of the fraction for a minute. And we need to think about large values of t. So as t tends towards very large values, or infinity, the denominator here, 1 plus a e to the minus bt, what's going to happen to that? Well, it's going to tend to be 1. Why? Because for very large values of t, we're going to end up with a very large but negative power, right? So, I don't know, let's imagine some number, maybe you've got e to the minus 1,000. It's tiny, 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 really tiny number times by a, but the whole thing is approaching 0, that there. Right? This is becoming incredibly small. Right? Therefore, inside the function, f of t will tend towards c on 1 plus 0, right, as t tends towards very large values, okay, and therefore, up here, f of t tends towards c, because c divided by 1 is just c, right? And that is our horizontal asymptote. I'm going to stop the video here and do the last bit, the second derivative, as a second recording, so this video is not too long.